Okay, good morning. Or, well, it's the afternoon now. Good day. For this one, I will answer everything else. So we only got through how many was that? Like three questions or four, I think. So I'll get through everything and I'll actually even re-answer this one because it was a bit unclear what happened. So let's just see. In here now, instead of the ideal Rankine cycle that we had earlier, now we have steam at 10 MPa. Oops. 10 MPa, 480 degrees Celsius, passes through a turbine. Everything is the same except for the fact that now our what do you call this? Our Rankine cycle now has state 1 being uh, a superheated vapor, right? So now instead of saturated vapor at 10 MPa, now you have 10 MPa 480 degrees Celsius. This would most likely indicate that this is a superheated vapor. So now we have this, and then it expands the steam to still the same condenser pressure, right? So again, we should draw the TS diagram, right? How much heat is transferred to and from the water in the boiler and the condenser, respectively. And again, we look at the thermal efficiency, right? So let's just finish this off. Passes through a turbine, expanding the steam to blah, 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 the condenser, okay? So much of it is the same. Actually, a lot of this is the same. And now let's just do it like this. And then, you know what, let's just draw it again, actually. Okay. And again, this is how I would normally draw a Rankine cycle when I myself am doing the computation. Like, I remember this is how I did it back then in METHER1. So the same way you guys did. And so I really am just like reliving my student experience right now. So we have the condenser here, and then the pump should be somewhere here. And for those who are wondering, like, why am I not putting the pump here so that it it measures, or right, it mirrors the four like corners of a rectangle, like 1, 2, 3, 4. My answer to that is that I don't know how to put a pump here, right? It's kind of awkward to have the pump doing like this, something like that. So that's why I prefer to just put it downstairs, right? So this is state 1, state 2, state 3, and then state 4. Back to the boiler. Okay? And again, our goal here is just to get all our values of H. Unless there are changes or mentions in speed or altitude, we're not going to bother with anything, right? This is our TS diagram, and our saturation curve is like this. That's weird. Okay, you know what? Okay, there you go. Close enough. Right? Let's draw the high pressure line here. High pressure line here. And then the low pressure line here. There you go. Everything's still the same, right? But now, what we're going to do is we're going to see just exactly how far, or rather how big the what do you call this? The effect is when now your steam is a superheated vapor instead of a saturated vapor. For state 1, we said that your pressure 1 is 10 MPa, or more specifically, right? You know what? Let's just put it here. Pressure 1 is 10 MPa, or 100 bar, right? And your temperature 1 is, what is that again? 480 degrees Celsius. The thing about this now is that you're not going to have to make this Kelvin, because, well, we're just going to have to go through, oops, we're just going to have to go through, what do you call this? The tables, right? The steam table. Sorry, I'm losing my train of thought a lot. So let's return. Let's have this, right? 10 MPa. So let's go to 100 bar here, right? And then let's look at 480. Now the enthalpy here is 3321.4. Now or 3321.4. H1, H2, H3, and then H4. H1, H2, whoops. What is that thing again? 3321.4. That's kJ per kg. And in this case, again, we're going to have to put your state 1 in the superheated vapor region. Now, I don't know if my drawing is correct. The thing about this is that I don't know if this will land here inside the saturation region, or maybe the superheated vapor is so high here that it will still land on the superheated vapor region for state 2. How will we know? The only way we can know is through identifying the fact that this is an isentropic process. And so we're going to have to, again, get the entropy at state 1, right? The entropy at state 1 will be 6.5282. 6.5282 kJ per kg. So, in this case, this is also your S2. 6.5282 kilojoules per kilogram. Let's see, our H2 will be depending on there you go, this, right? 0.06 bar gives us two values, which are still 0.5210 and 8.3304. The thing is that this is still in the middle. So, if you drop this down, if you drop this straight down here and then call this state 2, this is still correct, because at this stage, this will be, or rather at that point, that will be 0.5210. And at this point, this will be 8.3304. It's still in the middle. So what we can do now is we can try to calculate again for the value of x2. In this case, we will have 6.5282 minus 0.5210 all over 8.3304. 8.3304 minus 0.5210. This will be 8.3304.5210. That will be 0.7692. 0.7692. And in this case, we can compute for the value of H2 now via H2 is equal to HF plus X2 times HG minus HF, or again, right, HFG will work just as well. And if you remember, what was that? Like 151, was it? This one, right? 151.53, right? 151.53 plus 0.7692. And then our HFG is still 2415.9. That will give us a value of 2009.675. 2009.675. This is one of my pet peeves. Like, this third decimal place is a 5. I'll keep that there. I'll just keep that there for now. I don't want to round that up or down. And if we remember, right, this will still be state 3, right? State 2 still goes through condenser, so the agreement is that state 3 will still be a saturated liquid. And just like before, state 4 will also be the same state that we've had earlier. It's just that now it will take even more heat to heat up, right? It will take even more heat to heat up state 1 to the superheated vapor region. So in this sense, we can just copy from earlier our notes 151.53 and 161.59. 151.53 kilojoules per kilogram, and then 161.59 kilojoules per kilogram. Now, what were we saying? You should draw the TS diagram, how much heat is transferred, right? How much heat is transferred is going to be in the boiler. You will have, right? It's a good place, right? In the boiler, you will have going in state 4, going out state 1, and then going in as well the heat added. in this case, there's still no mention of a mass flow rate. So we're going to have to get everything in terms of per kilogram, right? This one is state 1. So whatever goes in, H4 plus QA, has to go out. It's equal to H1. Therefore, your QA is going to be H1 minus H4. In this case, 3321 minus this thing. So 3321, 0.4 minus 161.59, right? So our QA in here, you know what? I'll just put it here. Our QA value will be 3159. 3159.81. This is going to be kilojoules per kilogram. This is our heat added. And so if we look from earlier, right? If this is 3,159, how much heat did we add originally? 5. So about 2,600 compared to 3,160, right? So there's a whole, like 600. Yeah, there was a whole 600 kilojoules per kilogram that was added more just to get this increase right here. Okay? And so, consequently, the condenser should also exhibit this kind of property. What goes in is state 2. What goes out is state 3. And then what also goes out is the amount of heat rejected. Right? So this will have your H2. This will have your H3. And again, we see whatever goes in has to come out. So your QR value in here, you are assuming, of course, that it goes out. So this will be H2 minus H3. In terms of H2, we will have, what is that again? 2009.675 minus 151.53. You will now have, who am I to like mental math this? I haven't even eaten yet. Okay, 1858.145. 1858.145. You know what? Let's just round it off now. 15 kilojoules per kilogram. Right? This is how much heat you have consequently thrown out. So this is 850 compared to earlier, which is just 1,575. Right? So you can see the amount of heat that was thrown away more, right, does not beat the amount of heat that was used to heat the whole thing. But we'll see. We'll see in the end if the thermal efficiency does increase or if it does decrease. Let's see. The thermal efficiency is going to be your work net over your QA. But the thing is, we have no way of knowing the mass. So we'll just keep it like this. And again, work net is equal to heat net. So you can just say it's QA minus QR over QA. In this case, you will have 1 minus QR over QA. And so we will have 1 minus the heat rejected, 1858.15, all over the heat added, which is 3159.81. This is going to be 41.19% or 0.4119. So, what have we learned? Right? It is clear that according to this computation, right, our thermal efficiency has increased by a measly 3%, 3 percentage points, or 2.5 if we're being a bit conservative, right? Our percentage increased only by that amount, right? And that requires us going to, to superheated vapor territory, right? So for you to be able to boost your thermal efficiency, what you might want to do, or rather a good conclusion here is that for you to boost your thermal efficiency, use something that's hotter, which makes sense, right? Which makes sense. The hotter something is, the more energy you can extract from it. But you can see it's not by a lot, okay? Because the more you the more you heat, the more you throw away as well. Okay? So in that sense, there you go. This is for problem. I don't know what problem this is actually. Now here we have this whole thing, right? We have this whole thing. A power cycle receives heat via a reservoir at 1800 degrees Kelvin and rejects heat via another reservoir at 600 Kelvin. So it's a power cycle we're talking about, and it receives heat via a reservoir at 1800 and rejects heat at another reservoir at 600. Which of the following cycles are impossible and which are Carnot cycles? Okay? So, we have 1800 and 600. Right? Which of the following cycles are impossible? Let's just see by looking first at the different reservoirs, the two reservoirs for this power cycle. It seems that the thermal reservoir, the high temperature thermal reservoir, is going to be at 1800 degrees. Sorry, 1800 Kelvin, no degrees. Right? And then this one is going to be at 600 Kelvin, which is still pretty hot. Right? And so, under perfect conditions, this represents a Carnot engine, right? And under perfect conditions, the NTH max would just be 1 minus TL over T high, right? So this will be 1 minus 600 over 1800, which will give us indeed 2/3 or 0.6667. That is the highest that you can go. And according to Carnot's theorem, right, no other cycle, no other power cycle under these same conditions, aka 1800 and 600 Kelvin, can work better than the Carnot cycle. So let's first find out if these cycles are possible, if at all, right? QA is 500, right? Your QA is 500. Let's just, do this, right? What comes in is 500, and what goes out apparently is 100, right? Is 100. Therefore, what should be conserved or converted pala. There you go. That's the better word. What gets converted is 400 worth, right? And now we see, okay, all right. What we can do here is we can apply the NTH formula, the thermal efficiency formula, which is again work net over Q added, or in this case, what you can do is just literally put it all together, 400 all over 500. This gives you 80%, which is unacceptable, right? This is impossible under the second law of thermodynamics, right? More specifically, a restatement that is Carnot's theorem, right? A restatement that is Carnot's theorem, right? This is bigger than your NTH max, which makes it impossible. Okay? Now, for letter B, here is the what do you call this? A bit of a confusing question, right? We said that your QA, the heat added, is going to be 500, and then the heat rejected will be 200. So you're going to expect that, okay, right? This is going to be 300, right? The work net here is going to be 300. But the thing is that your work net is 250 for some reason. Right? So it seems like there is something that was not accounted for, right? 500 is not equal to 200 plus 250, right? That's only 450. So it seems like there is a certain 50 kilowatts that was suddenly gone, right? And the thing is, the justification here is that some of that 50 is most likely just lost inside the system as either frictional loss or basically any other kind of unaccounted for loss, right? Some kind of unaccounted for loss. That would make this the only kind of useful work that was converted. So actually, this is kind of work, kind of heat, right? We don't know for sure, but all we know is that it was not accounted for properly because this was not useful, right? This 50. And so, what we can do is we can defer to our formula, work net all over QA, which is going to be 250 over 500, which makes this 50%, which is still pretty high, but this is under right? This is under the thermal efficiency maximum set by the Carnot cycle. So this is completely fine, right? This is completely fine. For letter C, right? For letter C, now we will have QR equals 150 kilowatts, right? 150 kilowatts. 150 kilowatts. And then your work net is 350. Now, you might be thinking, okay, maybe there are also unaccounted for losses in here, but we don't have enough information to say that for certain, right? So in this case, we don't have anything better to do. We might as well just say, or rather, if there was nothing stated, then let's just assume the ideal here, which is going to be that this is 500, which is 350 and 150. Okay? And so again, right, under the thermal efficiency formula, we will have work net is all over QA, which is going to be 350 over 500, which is going to be 70%, which is again breaking the thermal efficiency maximum set by the Carnot cycle, which means this is impossible. That means that cycles A and C are impossible, and cycle B is just your run-of-the-mill cycle, right? Okay? It's just your run-of-the-mill cycle. Now, we will have this one. A Carnot cycle operates between two thermal reservoirs at 1200 Kelvin and 500 Kelvin. If used as a power cycle, what would be its thermal efficiency? If used as a refrigerator, what would be its coefficient performance? And if used as a heater, what would be its performance factor? Right? Right? So in this case, well, much of the same here, right? We will just create a Carnot cycle. You know what? Let's give them some space here. Maybe just here. Okay. Let's have this thermal reservoir to be at 1200 Kelvin. And this thermal reservoir to be at, what is that again? 500? Yeah, 500 Kelvin. Let's just, I know, here. There you go, here you go. And then a Carnot cycle. Oops. Carnot cycle operates between two thermal reservoirs. If used as a power cycle, if used as a refrigerator, if used as a heater, right? What would be its thermal efficiency? What is its coefficient of performance? And what is its performance factor? Okay? So in this case, we will have the Carnot cycle here. Carnot. Right? Perfect. Absolutely perfect. We will have here QA. We will have here QR. Right? And we will have here work net. Right? In this case, right? In this case, we just said, or rather, in our discussions, we were saying that there are special considerations for the Carnot cycle. More specifically, is that your QA is just TH delta S, and in here your QR is going to be TL delta S. This is for a power cycle, right? Power cycle. Okay, and in this case, therefore, we can see that whatever goes in must come out. So in this case, your W net would be QA minus QR, right? Which is also your heat net, which is going to be TH delta S minus TL delta S, or if you group the delta S's out, TH minus TL over delta S. So I'm just doing the thing again, or rather, I'm trying to rederive the solution to your Carnot efficiencies, to your first law for cycles in here. Okay, and now our thermal efficiency will be, right, work net over QA. In this case, this will be TH minus TL delta S all over TH delta S. We can now cancel. Even if we don't know the value, well, that's a number, right? And the numbers are present in both the numerator and denominator. And now we will see this is TH minus TL all over TH. Or what you can do is you can separate the two, right? You will get 1 minus TL over TH, which is the classical Carnot thermal efficiency. So in this case, we will just put in the givens. 1 minus 500 over 1,200. This will give us 7 over 12, which is, I don't know. I don't want to mental. 7 over 12, which means 58.33%. 0.5833. Here you go. And now, the next two, right? The next two have to do with reversing this Carnot cycle, making a reversed cycle now. A reversed cycle will just literally reverse a lot of things, right? Not reverse the not reverse the what do you call this? The reservoirs, more just like reverse the direction of your heat flow, right? 1,200, 500, and what you're still going to get here is a Carnot cycle. Let's try and make that more circular. There you go. Carnot cycle. But now it's reversed. So in this case, instead of this flowing down, this will now flow up. This is where you reject heat. And instead of this flowing down, this also flows up. This is where you add heat. And instead of this going out, this will be the one going in because you're going to have to give it work. Right? So in this case, now our QA is going to be the TL delta S. And then your QR is your TH delta S because it's now it's now making a cold thing colder and it's making a hot thing hotter, right? And as a result, your work net, right? Your work net is going to be what? Based on the first law of thermo, again, whatever comes in has to come out. So in this case, again, your work net is going to be equal to QR minus QA, or in this case, QR minus QA is still going to be, well, basically the same. But now, this we know to be negative, right? This we know to be negative because this is a reversed cycle, right? This is now negative. Meanwhile, this is positive, okay? So that can only mean that the changes in entropy are positive and negative respectively, right? Power cycles are positive, reverse cycles are negative. Okay? So in this sense, the COP cares about the work, the heat that you add per work net. So in this case, we will have TL delta S all over TH minus TL delta S. We cancel. We will see that this is TL over TH minus TL, which is going to be, what is this again? 500 all over 1200 minus 500, which is going to be 5 over 7. That's very bad. 142,857. 0.7? Is that right? 0.7142. Oh, yeah, 7143 pala rather. 0.7143. And, well, this is bad, right? Why is this bad? Because, look, it's not a good refrigerator, right? It's taking in 500. If you're taking in 500, right, you need even more than 500 just for you to make it work, which is not very great to hear, right? What you want is maybe to switch these values, right? Maybe make it such that if you get 1, instead of getting 0.7143, you get, well, I don't know, 3 or 5, something like that, right? But in this case, well, we're just computing naman. This is our lives are not on the line, right? For COP, what you should remember is that this is for cooling. Meanwhile, for the performance factor, this is for heating, right? This is now going to take into account how much heat you throw away or reject to the hotter environment, which is now going to be TH delta S all over TH minus TL delta S. And now this will just be cancel. TH all over TH minus TL. So be 1200 all over 1200 minus 500, and this will be 1.7143. Okay, this is now our answer, and those are our answers actually, right? So you can see they're very simple because of the fact that it's a Carnot cycle. When everything is perfect, right, things become very simple. Of course, the complications begin when it's not a Carnot cycle, right? Look at what a Rankine cycle, look at how much effort we need just to solve a Rankine cycle, right? Next, let's have, prove for any reversed cycle that your PF, your performance factor, is equal to your COP, your coefficient of performance, plus 1. If you're wondering, I did not touch my calculator for this last part, the performance factor. I just knew that performance factor is COP plus 1. So very technically, if you are pressed for time, you don't need to go through all of this solution. No, you can just add 1 and then have you say, okay, that's my answer. And I would mark it correct, right? Because this is supposed to be a property that is held, period, right? How do we prove this? Well, we're supposed to go to the most general definition of a performance factor and of a coefficient of performance. In here, a performance factor is QR over work net. Meanwhile, a COP is going to be a QA over work net. For a reversed cycle, we're supposed to have heat go up and then go out here. And that requires us to do work, right? That is the work net. So in this case, we will have a definition, or rather we will have an application of the first law of thermo, which is everything that goes in must go out. QA plus work net is equal to QR. Okay, so now let's just try one of these things. Let's try the right hand side of the equation, right? Let's try COP plus 1. That should equal, I don't know yet if it equals your performance factor, but it should. The COP is defined as QA all over work net, and then that should be plus 1 is equal to PF, right? We still don't know, right? Then I will try to make this, into work net over work net. So now we will have QA plus work net over work net. Okay, everything's still good. I still don't know if this is going to be PF, but what is QA plus work net? That's going to be equal to QR. And based on the definition of the performance factor, that's going to be QR over work net. That proves our point, right? Your PF is QR over work net, and this is the answer to prove this, right? If you're being asked to prove this, I just want to see these lines, right? I just want you to understand that you're going to have to use the most general formula. This also works for a Carnot or a reversed Carnot kind of cycle, but you probably shouldn't use, and you should not use, a more specific kind of formula for something that should be any reversed cycle. They say in here that this should be for any reversed cycle, right? So if you want to use Carnot, you only proved that it's true for a reversed Carnot cycle, right? We want to go a bit more general. Okay. And then we will have, this one. I like this one. Power cycle 1 receives heat QA to generate work W1 and reject heat QB in the process. Power cycle 2 then receives this waste heat QB, as an input to generate work W2 and reject heat QC in the process. If eta 1 is the thermal efficiency of cycle 1 and eta 2, that should be eta 2, of course. Right? This should be eta 2. Okay, I'm not gonna use that. Should be eta 2, right? There you go. And eta 2 is the thermal efficiency of cycle 2. What is the efficiency of the overall bigger power cycle in terms of eta 1 and eta 2? And if you guys are seeing in your problem set 6, I'm putting in a lot of mathematical manipulation for you guys to get some practice in terms of manipulating different aspects of the cycle, because it's important, right? Like for example, look at this number 3, right? Suppose the power cycle has a certain thermal efficiency of eta. What is everything in terms of eta? Just so everyone is aware, right? Where is that? Yeah. So it's full of those things. So be prepared to experiment in case you are not yet confident with your math or algebra skills. Just go ahead. Just experiment, right? Okay. Now, in here, oh, right. That's why I wanted to show you. Where is that? Ito, the number 7, right? Number 7. This is very interesting. Okay. Okay. Yeah, we should begin. And let's begin, actually, right? Let's begin in the sense that we should just put everything into a drawing or a figure, if you would like, right? I'm the type of person, and I feel like a lot of engineers naman are the kinds of people who would like to take things into a figure just to understand things a little bit better, right? The thing is that a lot of people are also a bit intimidated by the fact that, well, we have here a bunch of variables, right? So if we have a bunch of variables, it seems very daunting, right? Sabi natin, we have here power cycle 1 receives heat A. It receives heat A, QA, right? To generate work, W1. Okay, seems simple enough, right? W1. And then it rejects heat B, QB in the process. But then, see, power cycle 2, it's the one to be able to use this waste heat to generate a certain amount of work as well, work 2. And then it's going to throw away heat QC, right? Heat QC. If the thermal efficiency of this thing is going to be, eta 1, and the thermal efficiency of this thing is going to be eta 2, right? What will the combined cycle's efficiency be, right? If we were to combine these two into a certain system, right? Into a bigger power cycle, what it will do is that it will take in, right? It will take in heat QA, because essentially we're obscuring what happens inside here. It will generate two different kinds of work. It will generate work 1 and work 2. And then it will throw out waste heat C. So now we are asking, what is the efficiency of this in terms of eta 1 and eta 2, right? So this feels a bit daunting. How many variables do we have here? We have 1, 2, 3, 4, 5, 6, 7. And then you're solving for an 8th variable. So it seems very daunting, but I assure you guys, with enough practice, and if you take it slowly, it's going to be okay. All right? Now, let's try to connect a few things together, right? Let's try to connect a few things together. What we should connect here first are the cycles by themselves. Let's have here first the definition for eta 1. We say that this cycle has a certain efficiency. And how is efficiency generated, or how is efficiency defined again? It's going to be the work net. So it's going to be work 1, right? Work 1 all over the input heat, which was QA. And moreover, this also applies for eta 2. In this case, it generated work 2, and then it used as an input heat B. So these are your different definitions for for eta 1 and eta 2. Okay? Everything's good so far. So then what exactly are we trying to get in here? We're trying to get the full eta. So in this case, we are trying to get, right? How much work was actually done, right? Or how much work was essentially acquired, right? Versus the amount of heat that was added. In this case, the amount of work that you generate is work 1 and then work 2. But the amount of heat that you added was only QA, right? The amount of heat that you added was only QA. Why is that? Because literally, this created this and threw out this QB. The QB, it just so happens, was hot enough such that it was still a viable source of energy, such that you can create a value, a new kind of work 2. So in this case, you can see this, right? And what you can do furthermore is you can say, oh, I can just split these two, work 1 over QA plus work 2 over QA. What do you have in here? What you have in here is the same thing as your eta 1, right? This is just a value of eta 1. We're getting closer to our goal. The only thing that we need to know now is how do you do this thing? How do you do this work 2 over QA? So if anything, if we are a bit lost in here, we should just try to understand, we should just try to understand how these energies are related. So what we can do is, well, we can just use the second law tuloy, the first law, right? We can use the first law for so many processes, or basically so many systems in here. We can use this. We can use this as a system. We can use this as a system. We can use everything in here as a system, but let's just pick and choose, right? Your QA, let's just use this system first. Your QA plus work 1, your whatever goes in, right, goes out. So your QA is the thing that goes in, and whatever comes out is work 1 plus QB. And if we look now here, whatever goes into here should go out as well. What this means is that your QB is equal to work 2 plus QC. Okay? Now, what are we going to do? Well, it seems like we're no longer any closer to W2 over QA. But in this case, I would like you guys to consider trying this comparison out for yourself, right? What does this kind of look like? Well, I would say this kind of looks like eta 1 in the sense that the denominator is QA. This also looks like eta 2 in the sense that the numerator is W2. So in this sense, I also invite you guys to play around with this. Right? In this sense, what you're going to see is that if you multiply both sides of this by QA, what you will get is work 1 is equal to QA times eta 1. And what you will get here, if you multiply both sides by QB, you're going to get work 2 is equal to QB times eta 2. Okay? And now, what's happening? I still don't get anything. The thing is that if we're struggling, if we're trying to grapple for the relationships between things, we might as well just continue experimenting. How are you going to get this? Or how are you going to get these two equations to come into this equation here, this relationship or this function, W2 over QA? And basically, I don't know, I'm just going to try to replace different things in here. What we're going to see is that, I think I know what can happen. I think I know what can happen. Look at this, right? Excuse me. Right? What if we try and say that your QA is going to be equal to work 1 plus QB? I don't know. I really have no clue, right? I really have no clue. What if maybe we plug this into here? right? What's going to happen then? Okay, let's just try that out. We will have WA is equal to work 1 plus the value of QB, and here is work 2 plus QC. What do you guys notice this is? This is the first law for this bigger, right? For this bigger system. Whatever goes in has to come out, right? Whatever goes in must come out. So, nothing is being broken here. Nothing is being broken. But more just like in the sense of what are we going to do now here, right? What are we going to do now here? Well, we keep experimenting, right? If this value of W2 does not appear, right? Let's keep experimenting, right? In this case, maybe we can make this happen, right? Maybe we can make this happen. Okay. If we're going to transform our W2, let's just, you know what, play with it here for now because this is our target, right? Let's say that our W2 is QB times eta 2. QB eta 2 all over QA. Okay. What else are we going to do? Right? What else are we going to do? Maybe if we can create a relationship between QB and QA, maybe that can work. And look at this. If we can isolate QB in here, aka move this to the other side, we will get, right? We will get QB is equal to QA minus W1. Maybe if we put it in here, maybe something will happen, right? So I'm going to drop the value of eta 2 in here for now. QB over QA, right? Nothing is changing. And I will just put the values of QA minus W1 in here. That will be eta 2 and then QA minus W1 all over QA. And you can see, I can break these down, right? What will happen now is that your eta 2 will be QA over QA, which is 1 minus W1 over QA. It seems like we've just unnecessarily complicated this value even more. But do you see it? Right? This has already been defined to be eta 1. And so finally, there you go. Now this is our, right? Now this is our definition right here. Your value of W2, your value of W2 over QA is just going to be eta 2 times 1 minus eta 1. And if we now put everything together, we will have eta 1 plus, if we expand this, we will have eta 2 minus eta 1 eta 2. This is our answer. This is our answer for what do you call this? For this question, right? And so it's these kinds of major abstract questions that really will make you want to, like, I don't know, throw up, because there are so many variables floating around. The thing in here is that you're just going to have to really like claw your way through this, right? And it's these kinds of and it's these kinds of questions, it's these kinds of problems that help you understand the first law, right? And the second law just a little bit better, right? When you can create and when you can understand the relationships between these two, between these two laws of thermodynamics, that your skill improves basically, right? Ayun, I think that's the end of it. So, if you ever, this is for the mem people pala. If you are ever watching this, you know what? Let's have the real one for you guys, because you deserve that kind of celebration. If you're watching this, right? If you're watching this, and here, let's just put the presentation right now. We just solved for this, and there you go. Congratulations on finishing METHER1, Basic Mechanical Engineering Thermodynamics. I am very glad to have you guys as my students. This was a very fulfilling experience on my part. And ayun, if you guys have any questions so far about the other questions that we've just tackled, or the questions we tackled in class, just let me know. Okay? Thank you guys very much. I will be seeing you on quiz 3, right? On Thursday. Oh, sorry, on Wednesday. Thank you guys.